Okay, so we've got a second lesson of this area of study. This one's going to be on the quantum nature of light and matter. That's the best title I could think of for it because it covers few different ideas and they all kind of interweave together under the banner of quantum nature of light and matter. And it'll make more sense if I just launch into it. So we looked at Young's double slit experiment, and like I said a few times, this area of study, it used to be one with the previous area of study. We looked at light and matter and waves all in one hit. Now it's two areas of study, so we're going to kind of interweave the stuff we did previously into this topic, just go back so we can contrast what we've covered with the new stuff. So in Young's double slit experiment, we can see light diffracting and interfering. These are wave-like behaviors that you can't explain by the particle model of light. In a photoelectric effect, light's behaving as a particle in a way that you can't explain using the wave model of light. So two experiments with contradictory results. One says light's got to be a wave, one says light's got to be a particle. And because of that, we say that light has wave-particle duality. Covered that last time, but repeating it now, behaving as both a particle and a wave. So then a guy by the name of Louis de Broglie came along, and he suggested that since light displays the properties of waves and particles, well, matter itself might also display the properties of waves, because we think of particles and waves, and we think of particles a particle and waves a wave. But if light can show behaviors of both, why can't particles? So that gets encapsulated by what we call the de Broglie wavelength. Symbol lambda there. You've seen lambda for wavelength a million times before. That's equal to Planck's constant, which is going to have to be in joule seconds when we do this calculation. It's not going to work with the electron volt second version of it. And P is the momentum of your particle. So we can get out a second version of the equation where we've got lambda equals h over mv, because P equals mv, momentum equals mass times velocity. That's just this equation with the momentum replaced with mv, just because that's probably how you end up calculating it. You've got a particle, it's got a mass, it's got a velocity. What's its wavelength going to be? So I'll talk about exactly what that means in a bit, but just start out by doing a calculation. If an electron, like any electron, it's got a mass of 9.1 times 10 to the negative 31 kilograms, and it's got a velocity of 5 times 10 to the 7 meters per second. Speedy electron. What would its de Broglie wavelength be? So we can just grab our equation for de Broglie wavelength. H, Planck's constant, 6.63 times 10 to the negative 34. M is this, V is that. You plug that into a calculator and you get out 1.46 times 10 to the negative 11 meters. Now, what that actually tells us is that in order for electrons to do wave things, in order to diffract, which is like a characteristic wave thing that waves do, particles are not supposed to, in order for the electrons to show wave-like behaviors and exhibit things like diffraction, they've got to be interacting with scales of less than or equal to 10 to the negative 11 meters. So if they pass through a gap on that size, you're going to get electron diffraction. I'm going to talk about that later on. Well, they'll produce an interference pattern, but get into it later. Anything above that scale, you're not going to see wave-like behaviors. You shoot an electron, it does particle things, moves in a straight line, doesn't do any sort of diffraction stuff. So when I'm talking about electron diffraction, it's best illustrated using a diagram. So what happens is that electrons are sent through a very small gap, kind of like when we had our single slit experiment and a photon went through a single gap and we got a diffraction pattern on the other side of that gap. Electrons are shot through a small gap just like photons were, and that generates an electron diffraction pattern. It kind of is produced in steps from here to here. So it's a bit blurry up here, but what you can see down here is that when you shoot the electrons through a small gap, the electrons aren't going to just go straight through. So if you had a small gap and you shoot an electron through, classic physics, you'd expect the electrons just go straight through, hit your screen all in one straight line. What we get out is bright and dark bands alternating exactly like what happens when we did the double slit experiment. This might actually be a double slit diffraction pattern rather than a single slit, but the exact setup of the experiment is not too important. What matters is that you get these bands from your diffraction setup. And remember, it's got to be a very small sized gap, because if it's too big, you just see what you expect. Electrons go through and hit at the point where you'd expect them to. But with a small gap, you're going to get the electrons diffracting, and they're only going to really be in certain areas. You'll get electrons here but you won't get electrons here. You wouldn't see any electrons hitting this space. You'd see electrons here, but none here. You get bright and dark bands just based off where electrons are hitting the screen. So you've got like one dot for every electron. You're sending through a whole bunch of electrons and seeing where they land. That's what this diffraction pattern is telling you. So a light pattern, when you get something like that out from an experiment, you go, okay, well, it's a wave, obviously, so that's why it's diffracting. But when you're sending electrons through, you're not expecting particles to exhibit this sort of wave-type behavior. That's why it's a bit surprising that you're getting a diffraction pattern for matter, which is matter, not a wave. You don't expect it to do a wave-like thing like diffract, but that's what you get out. You get out this sort of diffraction pattern from electrons, from particles, suggesting that the electrons are, in fact, doing wave-like things. They are diffracting. Now, that raises a bit of a question, which is basically, well, I'm made of matter. If I'm made of matter, I've got a de Broglie wavelength, don't I? So if I pass through a gap, like I walk through a doorway, for example, why do I not diffract? Why do the particles in my body not all go off in every direction and form an interference pattern? So if I calculate my de Broglie wavelength, it's going to be Planck's constant divided by mass times velocity. I think I weigh like 75 kilograms. I haven't weighed myself in a number of years, so I don't know, maybe I need to update that. Let's just say I'm moving at a normal speed, a walking pace of about a meter per second. I plug those numbers in and I get out about 8.84 times 10 to the negative 36 meters. So I'm only going to diffract if I pass through a gap that's going to be less than or equal to 8.84 times 10 to the negative 36 meters. And I think the diameter of an atom is like 10 to the minus 10 meters or something like that. So I'm passing through a ridiculously small region, which I obviously can't do. I'm not that thin. But that's just why I'm not going to demonstrate wave behavior myself, because for that to happen, I'd have to have a large de Broglie wavelength, and just based off my large mass and my reasonably low speed, I'm not going to diffract. So I'm going to stay displaying particle behaviors and just do things that particles do. I'm not going to do wave-like things because I'm not going to be able to pass through such a small gap. So another aspect of this is that the experiments were done where they took electrons and passed it through a thin sheet of aluminium, and they got this diffraction pattern here. It's a diffraction pattern of electron beam passed into aluminium foil. They did the exact same thing using the same aluminium foil, but they did it using X-rays instead. So they were using particles here, they were using light here. And what you can see is these patterns, they're not identical, but they're very similar. They've got bands, particularly the outer regions, at about the same point. So how you'd read this is that before I had up this picture, bright and dark bands, this is kind of like what we call linear diffraction. I think that's the word, and it's not too important. The point is that we get straight line bands. We get straight line bright here, straight line dark there, and we get those kind of lines as our diffraction pattern. If you use different setups, then rather than just getting a straight line dark, straight line bright, you get circular bright, circular dark, circular bright. We call this a circular diffraction pattern as a result. So it's still a diffraction pattern. It's a circle one just because the setup's different, but it's illustrating the same sort of physics. And the main reason I brought these up is that the patterns observed are very similar in terms of their spacing between bright and dark bands, suggesting that the wavelength of the electrons in the experiment is going to be about the same as the wavelength of the X-rays, because if the wavelength of the electrons is about the same as the wavelength of the X-rays, they're going to display similar wave-like behaviors. They're going to diffract similarly if their wavelengths are about the same as each other. So wavelength of an electron, it's going to depend on its speed. The faster it's moving, the smaller its wavelength will be. But I think that's higher speed, lower wavelength. I'm trying to do this on the spot while I'm recording, so a bit of pressure. But that's just the gist of this, that we can basically compare these with each other by comparing their diffraction patterns. That allows us to say that their wavelengths are going to be pretty similar. And the last thing is that, well, de Broglie wavelength, lambda equals h over p. I'm still recording. And then, well, you can take that equation and rearrange it and get that momentum is Planck's constant divided by wavelength. And if we're talking about a particle, then that kind of makes sense in a way, because it's just taking this equation, which was for a particle, and rearranging that, which is nothing too weird. This equation gives the momentum of an object if its wavelength is known. Now, the reason that's significant is that light doesn't have a mass, and you know that momentum is P equals mv. So if you've got zero mass, you should, in theory, have zero momentum. So light without any mass would probably have no momentum. But according to this equation, if we take Planck's constant and divide that by the wavelength of the light, we're going to get out the momentum of a photon. So this is a bit of a different idea, the idea that light itself can hit something and transfer not just energy but momentum as well. We go back to the whole conservation of momentum. The photon's got some momentum, it hits an object, it transfers its momentum across. If we want to know exactly how much momentum a single photon is going to have, we can just calculate that by doing Planck's constant, which would have to be in joule seconds. We can't use the electron volt seconds one for this, divided by its wavelength, since we need standard units for an equation like this. So an example would be, what is the momentum of a photon with a wavelength of 10 to the negative 9 meters? Well, that's just a simple matter of plugging in numbers. P equals h over lambda, h over the wavelength. That gets us out a momentum of 6.63 times 10 to the negative 25 kilogram meters per second, which is a very tiny momentum. You'd need a lot of photons hitting something at once, a very high intensity, in order to get any sort of significant momentum transfer from the light to some sort of object. And you can use light to push on objects, very light ones. But like I said, it's just basically showing that you can have momentum for something that has no mass. It's a different way of conceptualizing momentum, just based off the idea of, taking the de Broglie's wavelength idea and just sort of running with it a bit. So I think that covers the 9.2 stuff today. It's a short lesson, so you should just be trying to get your textbook questions, and then ideally do your Ed Rollo ones probably before checkpoints. Checkpoints questions, I like them more, but I do need some way of checking that you're doing work over the next couple of weeks. So yeah, doing the Ed Rollo ones and just showing that you're engaging with the work in some way, that's something I also need to see too. But the text point questions should always be, I reckon, step number one, because they're just flat out good questions, good to start out with, even though sometimes they're duds, but overall that's probably where you want to start out. So 9.2 I think 10.2, I'm not sure, check the question plan. It's a 0.21 today, and that's just what you should be working on.